So I think let's just start the talk. So I think people already realize that there's a great empirical success for deep models. And this include like success in the different games and also success in vision, language, and also speech. But there's a big mystery in the deep models. The deep model is, if you ask people who are working on deep learning, then people will say, oh, I just fit a very big nonlinear transformations from input to output, right? So, but how this transformation actually works is a big black box. So in the first part of the talk, I'm going to talk about some of the recent work that we try to understand for deep learning trainings. So in my picture, so there's two components in and try to understand how deep learning works. So there's first is expressibility, right? So how expressible a neural network is for representing the data. So I think there's one famous paper that shows that neural network is a universal approximator, that you can approximate any kind of arbitrary data distribution with just one hidden layers, but with exponential number of nodes. Right, so that's the first part of it. This basically gives us the confidence that you can actually learn a neural network if your algorithm is smart enough. So the second part of how we train, how understand deep learning is through optimization. Right, so here we basically focus on, like, given the amount of training data, how can we train the model so that it goes to very small training errors. So in this part, there's different directions, like studying like whether we want whether the gradient is vanishing or exploding, right? So whether SCD or GD can go to global optimal, and how fast it is, the convergence rate. And finally, and that direction is we want to understand, even if we get zero training error, we get very small training errors, and what are the generalization properties of these trained models. And this is one of the major problems that in deep learning, because we all know that if we train with SVM, if we train with arbitrary data, train with like a boost, linear other boost, you can always find a zero training error solution. But then the question is whether how generalized it is. So in this talk, I'm going to talk about one of the recent work. So we start with this supervised learning, in which you have a data set that the data set will basically take, the network will basically take the input of data set and try to output point so that this point is similar to the labels y that is from the data set. So, but we can actually replace this data set with a student, a teacher, a network. So suppose you have a teacher instead, and this teacher has a fixed parameter, and the fixed parameter is basically a black box, and you don't have access to it. And the student is trying to learn from output of the teacher. So the reason why we can do that is in some sense, by the network expressibility. So this is because you can find a network that can explain the data set quite well. Then hopefully you can use that teacher network to replace the data set, and you can study the training procedure as well as generalization properties. So people might wonder why we want to study this student-teacher setting. I think from the 3 points that I just mentioned, so these three I can actually have, so with student-teacher setting, we can actually give answers to 3 of them. So first of all, from expressibility, we know that we can actually we know that there exists a teacher that can explain the data very well. So this basically gives you the foundation why teacher-student setting should work. And the second is, if you use teacher-student setting, then you can actually study very refined dynamics, behaviors by comparing the students' neurons with the teacher neurons. So this basically gives you additional information when you are trying to learn, we're trying to find what are the interesting properties. And then finally, in terms of generalization, if we can show that after training, the student can actually converge to a solution that is aligned with the teacher, then this actually will give you hints on generalization. Because if the students not only learn the output of the teacher, but also learn the intrinsic weights structure of the teacher, then we can expect that both teacher and students will output the same thing for unknown data. So there's a very old history of teacher-student setting. So in 1995, there's a paper, Online Learning in Soft Community Machines, by Saad and Sola, and they already studied this kind of setting, but in one-layer trainable parameter case. So in that case, basically, the basic assumption is if you put the input dimension to infinity, so this is what is called the thermodynamics limits, and in these cases, then you're going to see interesting properties. For example, if you further assume that the activation before the nonlinearity is Gaussian distributed, then you can actually solve the problem in analytical form by writing. You can write down the dynamics in analytical form, and these dynamics can give you a very good insights on how this teacher-student interact each other. And in some situations, students' nodes can actually be specialized, can show to be specialized to teacher node. But this specialization is shown basically with local linearized analysis. So in this talk, I'm going to talk about an extension of this, this work. And this is basically a recent work that we have been working on. So here we are, instead of using one-layer teacher, we're trying to use multi-layer teachers and also multi-layer students. And the students' network is over-parameterized in terms of it has a more parameter than the teacher network in each layer. So we are still using this L2 norm. And in this analysis, we think about finite input dimension, so it's more realistic. And also, this analysis should work for and the slightly over-parameterization. There's no crazy over-parameterization here. So the main question we want to ask is, with this over-parameterized student network, if we train the network until we arrive at a very small gradient during the training, will this very small gradient give you alignments between student and teacher? So if this is true, then if there's a small training error, then this will potentially lead to good generalization. So we are trying to move one step further into that direction. So before that, I'm going to talk about some very simple notations. So here's some notation. So we have two layers, L1, L and L minus 1. And the weights is basically WL between these two. And you have activation vector and the gradient vector by accumulating all the activations at different layers at the same layer together. So you have two two column vectors that representing these two activations of the same layer. So given all these notations, the weight updated rule is very simple. It's basically all the product between the activation of the lower layer, layer L minus 1, and the gradient that is sent from the top layer. And then you take expectation with respect to x. So for gradient descent, this expectation is taken over the entire data set. And for stochastic gradient descent, the expectation is taken over the entire batch, for one batch. So in order to do analysis, the first thing that we can do is to actually have the first lemma that actually establish a relationship between the student gradient and all the teachers' activation as well as the student activations. So this actually holds for arbitrary depths of value networks. So you can basically prove that by starting from topmost layer, and then you do a mathematical induction from the top layer all the way to the lowest layer. So, so basically, this is an interesting observation, and we can actually use that to show that the alignment would happen. So here, this A and B are two matrices that are piecewise constant. And this F and F star is basically the activation of the teacher, which never changes over training. And F is the activation of the student at that layer, which will change over the training. But this entire thing will be true for throughout the training procedure. So after we have that, then what happens is we can show that in the lowest layer, there will be alignments between teacher and students. But before we achieve that, we want to make some definition about different concepts. So first of all, what do I mean by alignment? The alignment here in the lowest layer, it can be visualized in this input space. So in this input space, every point is an input data point. And if these two weights are aligned, then basically means that the direction they're pointing to are the same. Or you can say in mathematically, there exists like a parameter gamma that Wj is equals to gamma times Wk, where gamma is a positive number. So this is a very simple definition of alignment. And we also want a definition of observation. So this will be necessary in a few slides. So in this definition of observation, so if the teacher J is observed by a student K, this basically means that the boundary of the teacher node have a non-zero intersection with the activation region of the student K. So that's a very simple definition. So after these two, I'm going to talk about the assumption. So what are the assumptions that will lead to this conclusion? So the first assumption is you have a region, and that region you will have a lot of data points. And here we basically assume there's an infinite amount of data points within that region. And we are still working on like finite data samples cases. So you can have like arbitrary sized regions. You don't need to have like a rectangle or convex regions. You can have like arbitrary, even disconnected regions. And but the key here is that the region needs to have interiors in order for this proof to work. So you also want to make assumption on the teacher network. So obviously, you cannot reconstruct the arbitrary teachers. For example, if all relevant nodes are dead in the training set, then there's no way you can reconstruct W1, W2 star. That's not possible. So we want to make these two assumptions. The first is in the lowest layer, there are distinct teacher nodes. So they are pointing to different directions. They are not overlapping completely. Right, so which can be satisfied in a trivial manner because we can merge all these teacher nodes that are same together. And the second is the teacher's boundary has to be visible in the dataset, which means that in the dataset there exists at least like one portion of the region that is on the negative part of the teacher, and another portion of the region that is on the positive part of the teacher. So after this, all this setup, then what we can say is given any teacher J, as long as it's being observed by an observer K, then there exists a student K prime that is aligned with it. So that's basically like the major, the main argument here. So here at the lowest layer, so if the gradient is 0, so for now I'm saying the gradient is 0. So people might wonder, okay, how about the gradient is small, then what happens? Right, so I'm going to talk about that later in the next few slides. But for now, let's say, okay, gradient is 0 for all the points in the training set. And it's 0 for all the input gradient of that hidden layer. And if the teacher node J is observed by student K after in this situation, then it will align. So why that's the case? So here's like a very simple sketch of the proof. The proof here is, first of all, because the gradient of the observer is 0 as well, the input gradient. So from this lemma, the lemma basically says that the gradient of this observer can actually be represented as a linear combination of the activation of the teacher minus the linear combination of the activation of the student. And this is 0 when we are considering the points that are inside activation region of the node K. So if this is true, then because values are linear independent, right? So because the value that is basically pointing to different directions, you can show that they are linear independent to each other. So this basically means that the coefficients for teacher direction must be 0. So what that mean? That means is if the teacher's coefficient is non-zero, there has to be a student that pairs with a teacher so that their combined coefficients is 0. So, and from this, you can actually see like why optimization can help, because you have more nodes in the intermediate layer, so they will serve as more observers. So as long as a teacher node is observed by one student, then this theorem will be applying. So do we have questions? Yeah. Yeah, so as I mentioned, it's for now it's infinite right now. So it's basically the region. Yeah, so we are working on like a finite set because the infinite, that's because we want, it's basically proved by contradiction. If this is not true, then there will exist like one data point within a region that has a higher gradient.
I mean, with infinite data set, it feels like a sort of topology that the algorithm.
Uh-huh.
Okay,
so if it's finite, then okay, if you want, I can give you some explanation on like how it is proved. Then maybe you can get more insights on that.
No, so ultimately, do you have finite?
I have 3 slides about finite set, if you want.
And it will be exponential and then the input dimension?
I don't think it will be exponential. It will be I think it will be polynomial. Yeah. Yeah. Okay. So I think I will talk about that later. I think if people are interested in the details, I will talk about that. So after that, then what happens is, so here's like a few examples showing why it is the case, right? So this is like one example showing we have a very simple 2D environment, 2D experiments. So you have two teachers that is shown by these bold lines. And you start with a bunch of teachers that are shown in these dashed lines. These are all boundaries of the railroad network. And after a few iterations, then what happens is you're going to see there's a bunch of students converge to the teachers. And there are two other students that are actually not aligned with any teacher. But interestingly, their outgoing weights are 0, are very small. So basically, like this is basically showing what happens if you have a student that is not aligned with any teacher. That's possible from this framework. Because from this framework, what we only say is for each teacher, there is only one, there's at least like one student that will align with it. Right? So, but there exists some students that is not aligning with it. It can be aligned with any random regions. But we can also show that for these unaligned students, that what happens is that their net contribution to these students to the output will be 0. Okay. So this is like another curve showing what happens for these alignments. So here's like each of the nodes represents like one student node. And each of the nodes, the x-axis basically shows that that's the normalized correlation for this particular student node to its best correlated teacher. So the y-axis shows that the number of the norm of the fan-out weights. Right? So this is basically the two axes. You can see this is going to be this kind of L-shaped curve, which basically means that a student node has to be either not correlated with anything, but its fan-out weights is small, or the student node is correlated with some of the teacher node, and their fan-out weights is large. So you can basically show this in multiple shapes, basically for multiple over-parameterization. So 10x means like a 10x over-parameterization. So you can also show this in a noisy case. So I think this is basically a more realistic case, because if you train with finite amount of time, then the finite amount of time, you don't really have a 0 gradient, right? But still, you can show that in the infinite number of sample case, you still have this approximate alignment. So this approximate alignment is basically shown by showing that there exists a teacher there exists a student that is sufficiently close to the teacher with their angle is small, that is on the order of epsilon to the power of 1 over delta. And also the bias is also pretty small with respect to epsilon as well. So if epsilon is small, then these two will go to 0, and there's a perfect alignment. So I think I'm going to show some of the detail of the proof if people are interested. Yeah.
So from this alignment, does it follow that the student is going to implement the same function? From your insights, like, do you have a corollary like that?
Yeah, so because this only aligns on the lowest layer, but not the top layer. So if there's the lowest layer, basically you only show there's in 2-layer setting, that's true. But in multiple layer setting, I don't know yet. Yeah. Yeah. So here's like okay, I will. Yeah, so so how to prove this? So if we start with noise, then what happens? So I think the rough idea here is first, this is the infinite sample case. So how you prove it? So if you have if this Wj, for example, Wj is some direction, that could be teacher direction, right? So if that direction is aligned with some other directions, then you are good. But assuming that if Wj is not aligned with any directions, then for each of this Wj prime, the boundary will basically intersect with the boundary of the value of this Wj, and this intersection will be small. in terms of because the more angle, the more difference in their directions, the smaller the intersection would be. Right? This intersection, if you assume that there's no direction that is aligned with the direction j, then this intersection will basically occupy a small fraction of the volume in this region. And because of that, then there exists at least like one node that is farther away from all these small regions. Does that, what that mean? This means that there exists a point that is in this boundary of the value of node j, but not in any boundary of the value of the other nodes, and they are far away from it. Because this is true, then what happens is you can actually pick 3 points that is vicinity in this region, so that these 3 points will be on the same side for all the neurons apart from node j. But there will be boundaries. These 3 points will be besides just close to the boundary of the node j. And you can basically show that there will be a contradiction in terms of their gradient, the magnitude of the gradient. Is that clear? Yeah. Okay, so that's the first thing. And the final sample case, I think we haven't put that into the archive yet, but there's some kind of very simple and sync analysis. In the final sample case, what happens is there's for example, there's a teacher boundary there, and you basically draw samples there, and this sample has to be independent of the teacher, otherwise they are cheating. But if you have sufficient number of samples, then what happens is you're going to have a number of samples that is within this region, and this amount of samples will be inverse proportional to the eta, right? So this is, if the eta is small, then this amount of samples will be big. But as long as you sample sufficient large, for example, you sample with 1 to the 1 divided by eta, then you're going to have a constant number of n eta within that region. That's the first thing. And the second thing is within this region, okay, I'm basically rotate that so that this plane actually facing you. So within that region, then what happens is you're going to have this counting argument. This counting argument basically says that do you have finite samples within this partial EJ, and that is within eta within to this region, then each of these like subregions, they also cover a small portion of the volume space. Right? So, if you compute this ratio between nj prime, which is the number of data points within each of the small regions, divided by the total number of points that is close to the partial j, then this number basically is proportional in expectation to the ratio of these two volumes. So, and if you have more samples, this will have a sharper bound. Right. And if the summation of all the probability distribution, the p is smaller than 0, there exists like one data sample that this will happen. So this and people may wonder like, so how many samples do you need to basically arrive at this sharper bound? I think this is basically intuitively. So what happens is you first need to basically place all the samples in the region first, and then you check whether this intersection between these two eyes, how many data points are there inside it, right? So, because this region is kind of like a regular region, then no matter where you are, if you have sufficient number of samples, the number of samples that you require is not exponential. It's only within this projective space. Is that clear? I may need to more explain. I'm running out of slides for this explanation, but this is like an ongoing work right now. Okay. If there's no questions, then we're going to the next slides. So for the next slides, we basically use the same thing to do this multi-layer alignments. So for the multi-layer alignments, what will happen is because of this lemma 1, we're going to have this alignments at the lowest layer. by using the same logic. The only difference here is instead of having alpha and beta, you have alpha x and beta x. And you have these two, and they are piecewise constant according to the lemma, and you can apply the same logic per region. So that's basically the way to show it. But I'm going to skip the details. And this is one of the experiments that we can do with 4-layer neural networks. So if you have 4-layer neural networks as a teacher and 4-layer networks as a student, then you can actually draw this figure at each level. Right? So for the lowest layer, what happens here is that there is so there's an air-shaped curve happening after a few epochs, and this air-shaped curve is pretty clean in the lowest layer. But once this lowest layer happens in this air-shaped curve, then what happens in the second layer is you're going to see this air-shaped curve happening at the same time, but it will be slower than the lowest layer. Okay. So with this, we probably can explain some of the phenomena that we have observed from the previous papers. So one of the very interesting things that we have seen here is there's actually a very interesting topology in the neural network architectures, neural network solutions. Two local solutions cannot be connected by a linear by lines. You're going to see there's a jump in terms of the error, but there will be these two will be connected by line segments. So this is actually a very interesting phenomenon you can see. But here's one explanation given the results. Then, for example, suppose you have two student solutions. These two solutions has a different kind of permutation in terms of alignments. So if you're directly connecting these two solutions together with a straight line, then what happens is you're going to see a bump in terms of the performance, in terms of the errors. However, if you do 3 segments in terms of the linear interpolation, then you're going to have a segment that has small errors in all the times because this V3, that's outgoing weights, they are 0. So you can basically change the direction of these weights to arbitrary directions without changing any loss functions. And then, because in the second step, both the first node and the third node, they have the same direction, W1 star, then you can actually swap their outgoing weights and without changing any loss functions. And then finally, you can basically change W1 star to arbitrary location, arbitrary direction that is not aligned with any kind of teacher without changing the loss function. So you basically have this kind of 3 segments, and you will have a path that has a very small loss function all the time. Okay, so and also the second part is the training dynamics, but here I'm going to be a little bit faster because there's another component that we want to discuss. So first of all, this critical points looks pretty nice, but can we achieve that via training with HGD? I think the answer is not easy. We have done some experiments for that. So first of all, I want to define what is a strong teacher and what is the weak teacher. So for the strong teacher, in the 2-layer setting, so we show the strong teacher is when the fan-out weights is large, and the small, for the weak teacher, the fan-out weights is small. So there's some slides showing the training dynamics of what happens for strong and weak teachers. We initialize the teacher so that the fan-out weights are bigger for teacher 0, and the fan-out weights are smaller in terms of norm for teacher 4. So you're going to see for each of the students, they will rush to the very strong teacher 0, right? But for weak teacher 4, basically for a long time you're not going to see a lot of group correlations until later when the teacher when finally there's a students that converge to teacher 4. So that's interesting dynamics, but I'm not going to show the theory there because here basically we are using a semi-empirical, semi-theoretical approach to study what's going on here. Okay, so let me find, so for field directions, there are a few things. First, for the training dynamics, what is the way to understand that better? And in the finite sample case, I will show there's initial steps for finite sample case, but we look like it's possible that we can write an Nelson bound, but it's still ongoing work. And also, there's some interesting questions like, so how this framework can explain adversarial samples, etc. Okay, so that's the first part of the talk. Any questions? Okay, if there's no questions, then I will go to the second part of the talk. Second part of the talk is more on the reinforcement side. So here, we want to understand the role played by neural network in prioritized search. So this is a joint work with one of my interns, and Li Xin, who is a professor in Stanford in Mass. So we all know that AlphaGo series has made a big success in terms of the performance. And in AlphaGo, what happens is we are using like a Monte Carlo tree search with neural networks. Right, so we basically start with the Monte Carlo tree search, the current tree, and then every time when you want to explore a new region of the space, that what happens is first like run policy network on the beginning at the starting point, and then the policy network will basically tell you the policy network will basically tell you okay, the preference of all the actions. So after that, you basically run your Monte Carlo tree search by doing this iteratively until you find the nodes, and then you call new value network. The network will basically tell you okay, what are the values it's like to be, and then propagate that value back and update all the statistics there. Right. So I think a traditional Monte Carlo tree search usually don't use policy value network. They start with a uniform distribution of all the actions, as well as using a random rollouts all the way to the end to get a solution. To basically get an outcome, and use that outcome as the value to backpropagate all the weights here. So, but in the AlphaGo paper, what they show is if you combine policy network and value network in the Monte Carlo tree search, this will definitely improve the strength of the bot. And definitely, what we could imagine is, given the same amount of training samples, the sample efficiency, the search efficiency is also improved. So in order to analyze that, we are trying to use a simple A-star model to analyze this kind of behavior. So for this model, what we are doing here is we still keep this tree, but instead of having a visitation counts on every nodes, we are trying to put all the nodes that hasn't been explored into this priority queue. And every time we expand a node, and we basically use a value model to find which node we want to expand. And second, after we decide which node we want to expand, we want to use a policy model to expand which node in which kind of order. And we basically do this kind of thing repeatedly. So with this A-star model, then what we can show is if the noise of these value functions will degrade when we are getting into a deeper and deeper tree, then what happens is you're going to have the number of samples that requires, or the number of neural network core that will requires to achieve the optimal action that will be bounded. And in some sense, it will even be polynomial rather than exponential. So the notation here is, so you have this tree, and k is basically the branching factor. Here we assume that the number of branching factors are the same for all the nodes. And you have a v. V is basically the true value of the state. So, and the true value is not visible, but instead we are using a neural network to predict that true value v. And this true value v is the true value v is not necessarily v star, because if you are evaluating a node that is not in the optimal path, that true value v will be smaller, and the gap is called delta. So, and between this v, which is the true value, and the value that is predicted by value network, there's a gap. And this also gap, this gap is called xd. We assume that this is an IAD zero mean random variable at depth d with sigma d standard derivation. So note that this XD is instantiated once for each value network call, and after that, it will be fixed all over the place. So we cannot get true value by repeatedly call this value network at a particular node multiple times to get the true value. That's not allowed. This is also true for the practical settings. So the key point here is like sigma d is actually decays over depth. Then like the question is how much it should decay so that you get a good solution. Okay. Any questions?
It's basically the random tree model in a way.
Okay. Yeah. Okay. Okay. So if the value network is, if you only have used value network, then what you can do is you can try to bound the expected sample complexity by the number. First is you have to visit like the path in the optimal search path, and also you have a lot of overheads. This overhead is because you overestimate the value function you overestimate the true value function by the current value estimator. And this will be basically the summation of all this overestimation, summing over the entire tree. So we want to bind this. In order to do that, we basically assume there's two neural network models. So first of all, we think about these constant gap models in which you have optimal path, and that optimal path has an eta as a value that is bigger than 0. And for the rest of the regions, all these v's are zeros. And there's another way we can model this neural network value function distributions by saying that you start with the v star, which is the current nodes, but for all the non-optimal paths, we are trying to add subtract by a delta, and this subtraction by a delta will be followed in the non-optimal path. So basically, like the lower you get, then the smaller a value it will be. Any other questions? Okay, so here's like the main conclusion. So if you have used value network only, then what happens is the sample complexity can be bounded by that quantity. For the C, there's an exponent, which is k to the power of C. So for that k to the power of C, that C has to be satisfying that condition. So if the sigma, the standard deviation of each of the layer is decaying faster than the square root of d, then what we can see is you can actually have a polynomial sample complexity because C will be a fixed number that is not dependent on the d. And you can also do the same thing for generative model. In that case, you also see very similar conditions that will lead to polynomial sample complexity. Okay. So we also did a few experiments with this kind of noisy models. So with a constant gap, we show that this algorithm 1 can be a little bit better than the minical tree search in the original minical tree search in these two different noises. And on the generative model, you can also do the same thing. And people might wonder, okay, what happens if we add a policy network? And a policy network can be regarded as a different set of value network. And by assuming that policy is basically a softmax, a soft version of picking like what action you want to take. The good thing about a policy network is you can get the value of all the policies in one network call, rather than having k different network calls to get the value function for all these s points. Okay, so here we assume that there is still a gap between the true values after you take an action to the policy network that is predicted from the current states. And because of that, what you can do is since you have this policy network, PSA, you can first sort that so that it is on this decreasing order. Then you basically check the gap between the policy and the first predicted probability and the case probability. And these two, if these two are there's a sufficiently large gap, then you can start expanding now. Because you know that after this threshold, the expected value is going to be very, very small, and that one is going to be not likely to be the right path to explore. Because of that, what you can do is instead of having the k term at the beginning, you can actually replace this k term as this complicated formula that shows that in some cases you can reduce the k exploration. So we also did experiments showing that it's still good by this compared to this PUCT, but the gap is actually not that big. So which shows that PUCT may actually have interesting characteristic that is not being modeled by the modeling procedure here. So we are still a little bit better, but not substantially better. So in terms of future work, so first of all, we want to add back this variation counts. So in this framework, what happens here is we are not using any variation counts at each of the node. We just replace the new value. We replace the old value of each node with the new value that you have explored under that tree. Right. So, and also we want to test it in the real games and the environments to see whether this new algorithm will work or not. Okay, thanks. There's the talk.